Okay, so in the last lecture we were discussing perceptron algorithm, and we saw that that perceptron algorithm was having a problem which we discussed. There were few problems, right? Last time we discussed the one of them was this particular problem where if the we do not know, like which will be the best hyperplane, by which is the best separating hyperplane which can separate these two data sets. So last time we saw that depending upon the initialization, whether you initialize at this point or you initialize at this point or wherever you initialize in the data set, finally when you solve the perceptron algorithm, then what you will get is the best separating hyperplane, which can be either of these set, which we had discussed last time also, right? So any of the solutions can be one of the solution for perceptron algorithm. But the problem that we discussed last time was that this particular hyperplane which we are discussing currently it's not a good hyperplane because it is very close to the data point. So this particular data point specifically, so if you add some noise in this data point, then what will happen is this noise can move this data point to this side, and because of which, if you are having this as your hyperplane, then what will happen is this particular data point which is belonging to y is equal to, let us say, 1 class, it will be predicted by this particular hyperplane as y is equal to -1 class. So that is the problem with this particular hyperplane. Similarly, other hyperplanes which are close to these data points are also problematic. So visually, if you see which is the best hyperplane among all these hyperplanes, all of you will agree that this is the best hyperplane among all the possible set of hyperplanes which are given here. And the fundamental reason for selecting this particular hyperplane among all the hyperplanes is that it is somewhat in middle of these two data points, two data sets, this data set and this data set. So somewhere this particular hyperplane is in the middle of these two data sets. So that's why you selected it, or you will be forced to, you will see that this is the best hyperplane among the rest of the hyperplanes which are available. But at the back of your mind, why you selected this hyperplane? You selected this hyperplane because your mind will observe that what is the margin of the point which is closest to this separating hyperplane. So you will see that the margin of this point from this hyperplane and the margin of this point from this separating hyperplane is maximum from either sides. Like from this side also it's maximum, from this side also it's maximum, it is somewhere in between. So basically it is maximizing the margin, and by margin means the closest point to the hyperplane, what is the distance between that is what we call it as a margin. So you are automatically selecting this, but at the back of your mind will be judging this margin actually. So if the margins are too large, then you will select this hyperplane. You will not select this hyperplane because the margin here is small, whereas the margin here is big. You can say, okay, one of the data points has a big margin compared to the other data point, then also it is okay. No, it is not okay. You have to have a maximum margin for both the sides of the data point. It's not like you will have a maximum margin for this particular set of data points, but for this you do not have any maximum margin. So you have to maximize the margin on both the sides of the data points. So that is what the concept of margin is, and that is what the topic of today's class is, that is support vector machine. So support vector machines are basically helping us to come up with this particular boundary which actually gives you the maximum margin from the closest data point. So this is the closest data point in this data set which is close to the hyperplane, and this is the, let us say, closest data point which is close to this separating hyperplane. So support vector machine will result in this particular margin which will this particular hyperplane which separates the margin to the maximum value. So that is the objective of this particular topic which we are discussing today, which is support vector machine. And lecture and group number 8, group number 8 people, are you there? Group number 8? Okay, so today's lecture will be drafted by group number 8, and the deadline for this will be the coming class, which is on Friday. So note that. So this is basically your margin. So the idea is you must be now motivated to understand that why we are understanding this support vector machine, and why it was not possible in case of perceptron algorithm. So this should make you clear enough to understand the topic of support vector machine. That is, the objective is to maximize the margin. So let us understand today the theory of support vector machine, which is a bit mathematical. So I will go step by step, and each of these points will be clear to you. In case if you have any questions, you can ask me in between. But today let us see what support vector machines are. And support vector machines are actually, in short, are also known as SVM. So today the topic is about SVM. So again, you can see here I am showing you two plots, and the data points are same, but in one case you will observe that is on the left side, you will observe that the for this particular data point, you can see the distribution of the data point on the left and right is the same distribution you have on the right figure. So the distribution is not changing, but what is changing is the separating hyperplane, which separates the two data points, which is this one and this one. So this is changing. In this figure it is like this, in this figure it is slightly changed to this. So you can see now that in the left figure, the margin of the closest data point to this particular hyperplane is this much, and the margin of the blue data point to this is this much. So basically this dotted lines are showing you the boundary of the closest data point to the separating hyperplane. And the margin that you will observe here is this margin. Let us say we call this as M1. Now what I do is I use this separating hyperplane and move it a bit. Like I'll move it towards the left side. So if I move it towards the left side, the new separating hyperplane becomes like this. So the new separating hyperplane, if it is this one, you can see now the margin that you are getting here is M2, and you can clearly see that this M2 is greater than M1. And how, if somebody can somebody might ask, right, why we are moving from here to here? We are moving from here to here through the optimization process. So if you recall, these separating hyperplanes are function of theta 0 and theta 1 or any other variables that are used to define this linear separating hyperplane. And you know that we vary these theta 0, theta 1 and theta 2 through the gradient descent. So once you vary the values of theta 0, theta 1 and theta 2, then the separating hyperplane will also change with the iteration. So at this particular iteration, you can see the margin is maximum, and we will stop our algorithm here. Whereas in this case, the margin is not maximum, and our algorithm will keep on searching for the point where your margin is maximized. So the concept of maximization margin is the basic objective of, this is the objective of support vector machine. So support vector machine, actually, the main objective of SVM is to maximize the margin. So that is what is the objective of SVM. So the questions that we need to ask here is, before going into the actual problem of support vector machine, we should ask three questions to ourselves. The first question is how to measure the distance of a point from a plane. That is what I am saying here, right? What I am saying is the distance of this point through the plane. I am saying that if this distance is maximum, then we will say that our objective of support vector machine is achieved. So we want to know that how to calculate this distance. That is important. So this is what our first objective is. That is how to measure the distance from a point to a plane. That is how to measure the distance of the point from a plane, this plane. Second is how to formulate this problem of maximize margin. So what we are saying continuously is max margin, we have to maximize the margin, we have to do this or that. From the very first beginning of this lecture, I am always telling you maximize the margin. So the question that is important is how to formulate this problem mathematically. Like you want to solve a maximization of the margin, but you do not know how to solve it. So we have to formulate the problem of max margin. And then once you formulate, then the question comes how to solve that. So we will go through all these three steps one by one. And once you finish off all these three steps one by one, at the end what you will get is this solution. At the end, once you solve this max margin problem, you will get the solution of the support vector machine, which is this hyperplane. So we will go one by one. Do not worry about it. You will able to understand this theory of SVM as we go slowly to understand what this is. So let us work on our first task, that is how to measure the distance of a point from a plane. So in this particular objective, let us define a theorem. And what is this theorem? And we will prove that theorem here. So the theorem is, let g theta be a linear discriminant function, and let h is basically a set of all points x such that gx is equal to 0. Be the separating hyperplane. So what we are saying is, let g theta be a linear discriminant function. So by saying means linear discriminant function means this is the same g theta which we were discussing earlier, right? Theta x dot theta plus theta 0. So this is the same g theta which, if you recall from our perceptron algorithm, we are actually using this as, and we are calling this as a linear discriminant function right now, which actually another way of saying that you are trying to discriminate between two classes. So this is another way of saying that it's a linear discriminant function. And what it is saying is that h is a separating hyperplane. By saying separating hyperplane means actually it is defining this plane which separates the two classes here. So what it is saying is, the definition of this plane is defined in such a way that all the values of x which are lying on this particular gx. So this equation, this is basically g of x. Then all the points which are lying on this x, on this g of x, such that when you put the value of x in this equation, its value will give out to be 0. So this is actually defined as h, another definition. So h is basically nothing but all the points x which are actually lying on this discriminant function g of x. So this is basically the definition. And then what we are trying to prove here is that theta divided by the L2 norm of theta is the normal vector of h. So what we have to prove is that you have this separating hyperplane, and we want to prove that this theta, which is coming out of this separating hyperplane, it is normal to this h. We want to prove that this is 90 degrees. And if you recall in the earlier lecture, I told you to prove it using the perceptron algorithm. When we were discussing the how perceptron algorithm works, I showed you and I told you that theta is normal to the separating hyperplane, and I told you to derive it. So this is the derivation for that. That is, theta is actually normal to the separating hyperplane. We will prove it today. And the second question is that for any value of x0, that is, you have a separating hyperplane, let us say this separating hyperplane. Then for any value of x0, so you have some data points, data clusters here. So any x0 you take, and what you want to know is you want to calculate this point's distance from this separating hyperplane. So this is important because you recall we are always saying these distances, right? These distances. So we want to actually calculate the distances of these points with the separating hyperplane. So that is what is actually given over here. So what we are doing is, for any value of x0, we want to calculate the distance of this point from the separating hyperplane, and this distance is actually given like this. What it is saying is the distance d between x0 and the separating hyperplane h is nothing but it is the discriminant function g theta, see g theta is nothing but theta 0 plus theta 1x plus theta 2x, so it is this discriminant function. So what you are doing is you are actually putting in this discriminant function x0. So you will do what? You will just write theta 0 plus theta 1. You have this sample, right? So you will put x0 here. So this is the point x0, and you are substituting this x0 in this g theta x0. And now you divide it by the 2 norm of theta 2. So this is the distance that we will calculate, and we will use this distance extensively in the derivation of the support vector machine. As you know that we have to actually somewhat maximize this distance, because we want to maximize this distance, right? Our objective is to maximize this distance. So we will do that using this particular expression. So we will see how we derive this and how we prove that theta is normal to the separating hyperplane H. So in the first question, where we have to prove that theta is normal to the separating hyperplane, in this case what you do is you take 2 points x1 and x2. So if this is your hyperplane H, so what you are doing, you are actually taking 2 points on the hyperplane, that is x1 and x2. So since both of these points are lying on the discriminant function gx, so what you will do is if you substitute the values of these points, that is 1, or you substitute the value of x2 here, its value will come out to be 0, because these are the points which actually satisfy this plane. So obviously it will give you a 0 value. So once you substitute these values of x1, x2 in the g theta xi definition, that is x1 and x2 here, what you get is you get these equations. One is for x1, another one is for x2. So once you have these two equations with you, then what you do is you equate the two together. So you equate the two together, and once you have this, you can actually manipulate the terms by taking this term this side. This will cancel out with this one. So once you have this, you will be getting this answer. So what it shows is that you are actually taking the dot product of theta transpose with x1 minus x2. So if you are taking the dot product of theta with x1 minus x2, what is x1 minus x2? x1 minus x2 is nothing but it's a vector which is connecting these 2 points, and then you have a theta vector which is over here. So when you have a dot product of theta transpose x1 minus x2 vector equal to 0, what it means is that it is making a 90 degrees angle with the separating hyperplane. So by this we can prove that theta is actually a normal to the surface. So this is the surface, your theta vector is normal to it. And if I want to make it as a unit vector, if I want to make this theta as a unit vector, what I will do is I will simply divide it by the norm of L2 norm of this theta. So your theta divided by theta transpose theta 2 is actually a unit vector. So I will show you here. So it's basically a unit vector, and it's basically equal to 1. So we are actually we are actually making it as a unit vector, and the value of that is theta divided by theta 2 transpose, L2 norm of theta 2. So you can see now we have proved that this particular vector, which is theta divided by theta 2, L2 norm of theta 2, it is making 90 degrees to the separating hyperplane H. So any questions here? Okay. So now our second objective is actually to calculate the distance. So if you recall our second objective, this is our second objective, right? This is our second objective, to calculate the distance of the point from the plane. So we will calculate this now. So the distance of the point to the plane can be calculated like this. So let us say you pick a point xp. So this is the point xp, you have picked it on hyperplane H. So this is your hyperplane H. You are picking a point xp on this H. And then this point xp is nothing but it's a projection of this x0. So you have different data sets cluster here, right? A cluster of data set here, right? So from this you are actually taking a simple x0 from this data cluster and you are projecting it onto the separating hyperplane H, and this is the orthogonal projection. So you are taking a orthogonal projection, you are not taking any other projections like this. These are not valid projections because they are giving you the maximum distance. So we are not taking all these projections, we are only taking the orthogonal projection onto the separating hyperplane H, as it is the shortest distance. So we want to know what is the shortest distance of this point x0, which is the data cluster point onto the separating hyperplane. So the basic as we have taken the orthogonal projection, so what will happen is the difference of these two, that is the x0 minus xp will be a vector. The difference of x0 minus xp will be a vector in this direction, and this direction actually it's a normal direction because you are taking orthogonal projection onto the separating hyperplane H. So what you can do is you can actually write this vector in terms of this vector, which is a unit vector, by scaling this vector by a factor of beta. So you can see the direction of this vector and this vector are same. So if you want to write this vector in terms of this vector, then you can do what? You can actually scale this vector by a factor of beta up and down, and you will get the vector which is in the same direction as this one. So this is what you are writing over here. So you can see x0 minus xp is the vector which you have this one, and you are writing it in terms of a unit vector this one, and you are scaling it by a factor of beta, which either scales this particular vector towards whether it will shrink or expand depends upon the data point x0, whether it is at this point, or x0 is at this point, or it is at this point, and it is at this point. So you can scale this vector as per the factor beta multiplied with this unit vector. So this is your beta. So what we have done, we have represented this vector as beta times multiplying with the unit vector which is here. And another important thing that we know is that xp actually lies on this separating hyperplane. So if xp lies on this separating hyperplane, then it's very easy that if you write it into the equation of g theta xp, then this will be equal to 0. As simple as that, because this point satisfies the separating hyperplane. So once you put the value of xp into the separating hyperplane, you will get this answer. So once you have this, what you can do is you can also calculate the x0 onto the separating hyperplane. You want to know, you just want to put you just put x0 onto this equation of the separating hyperplane. So what you will get is you will get this answer. As simple as that. This is x0 here now. Earlier it is xp. And note that this value is not equal to 0 because x0 is not lying on the separating hyperplane, so its value will not be 0. So now what happens is you can write x0 from this as xp plus beta times theta divided by theta 2, L2 norm of theta 2. So what I am doing, I am writing x0 as xp plus beta times theta divided by L2 of theta. So this from here, and then you have this. Now what I am doing, I am just putting it over here, and this theta transpose xp is this, and then we have beta times theta transpose theta divided by theta 2. So this you already know, it is basically g of xp. So g of xp is, we have already calculated, and that value is 0. So if this value is 0, this is gone as it is 0, and then we have beta times theta transpose theta divided by L2 norm of theta. So this is nothing but it's theta 2, and once you divide by this, you will get this. So the value of beta comes out to be this. So we have proved that this is the distance d, this is the distance d, which we were looking for, which we wanted to prove here. So if you recall, this is the one which we wanted to prove, and this distance is the d. So this is basically the expression for that. And if you want to calculate the location of xp, it is as simple as that. You just put the value of just a second. So what we were discussing is that we wanted to know this xp location. So what we are doing is we are just putting x0 minus beta. You already know this beta, this is there, right? So we wanted to actually substitute here. So beta we have already calculated, and we want to substitute that value of beta here. And once you substitute that value of beta here, which you have calculated just now, you will get this expression. So this is basically, the position of the point P. This is not that important, but just wanted to show you that you can, get the location of the projected point xp, which is actually the projection of x0 onto the hyperplane, by, getting these equations. So that is a different story, but this is what you have here. So now we will use this particular thing extensively. This is the distance of the point from the hyperplane. So we will use this because, the concept of maximization of the margin that we want to do in case of support vector machine actually will be coming by using this particular expression. So now we are defining two important concepts. One is the unsigned distance. So what is unsigned distance? Unsigned distance is nothing but it's a distance of the point xj from the cyclic hyperplane, which we have already calculated. So we are calling this as unsigned distance d of a point xj from h, which we have already calculated. And what we are doing, we are actually taking modulus of this distance. So the distance which we have calculated here, right, this one we are taking just modulus of it, and we are calling it as the unsigned distance. And note, this is xj here. So because we are actually finding out the distance of a arbitrary point xj. If it is x0, then 0 will be here. If it is 1, then it will be 1. Then here it will be 1. That's why a generalized value will be xj. So this is basically a unsigned distance. So if you want to see graphically what this is, then you have these data points. One data cluster is this one. Another data cluster is this. The class for this data cluster is +1, and the class for this data cluster is -1. So if I want to calculate the unsigned distance between these data points, that is this point distance from here, this point distance from here, or this point distance from here, or this point distance from here, or for all the data points, then it is actually represented by d of xj comma h. And you will as you are taking the modulus of it, then what happens is you are getting a positive value. If you do not take the modulus, what will happen is in this particular thing, if you put the point on this line, it will give you a greater than 0 value, and if you put these points onto this equation of the line, it will give you less than 0 value. So this is simple geometry, like coordinate geometry. If you must have done to determine whether the point is to which side of the line, what you do is you put that point onto the line, and if that value gives greater than 0, you say it's on the right side, and if it is negative, then you will say it's on the left side. So similar thing is over here. So all these data points, which will, if you put these values into this equation of the line, if it gives you positive value, then it is on the right side, and if it gives you negative value, it is on the left side. So similarly, if you see here, what you are doing, you are actually putting all these points in this equation of the line, which is actually nothing but g theta dot. So you are putting the values here, x1 or x2 or x3. You want to check whether this value gives you greater than 0 or less than 0. But actually you have taken the modulus, so it will always give you a positive value. So this positive value is called as unsigned distance. So the margin, what we were discussing, like we want to maximize the margin. If you recall, we want to maximize the margin. So margin can be actually represented in terms of unsigned distances as gamma. So we are calling it as margin, which is gamma, which is minimum of all the distances that you will calculate. All the unsigned distance, note, it's all the unsigned distances that you will calculate for all the data points from the separating hyperplane, and then you are taking minimum distance among all of them. So if you see from this diagram, this is the minimum which you will get, because all the other data points are larger than this gamma. So you will calculate all the distances, right, from this separating hyperplane, that is, and you will take the absolute value of these distances, and then you take minimum out of that value is given by gamma. And this is what we are calling it as margin. And we want to actually maximize this gamma. This is our objective. If you recall, when we started our discussion, we wanted to maximize gamma. So gamma is here. So gamma is actually a function of theta and theta 0. Why it is a function of theta and theta 0? You can see that gamma, you will have h here. H is as a function of theta and theta 0. So if your h actually changes from here to here, you can see, and why it changes? It changes because during the optimization you will change the value of theta and theta 0. So this separating hyperplane will change to this direction. If this separating hyperplane changes to this direction, your gamma will change. So that's why gamma is actually a function of theta and theta 0, which are the parameters of the separating hyperplane which you are trying to optimize. And gamma is actually greater than 0 always, because you are taking the absolute value, right? So you are taking the absolute value, so it will always be greater than 0. And it will be equal to 0 when the data point is on this line. If the data point is lying on this line, you know that equation will be returned to be equal to 0. So this value will become 0 only when xj is on the boundary. So note that gamma is basically a unsigned distance which is minimum. So this is the expression for gamma. And you will come to know in the later slides, we want to maximize this gamma. We want to maximize this gamma because we want to do a maximization of the margin. That's why we want to maximize this gamma. So next we define another important concept, which is signed distance. Signed distance is nothing, but you will just know in a while. The problem is that earlier distance which we were using, it is an unsigned distance and that distance cannot actually tell whether the point xj is correctly classified or not. We will discuss it in a coming slide. That is the problem with signed distance. That is, this gamma cannot tell whether the point is correctly classified or not, whether it's on the correct side or not. Only the signed distance can tell whether the point is correctly classified or not. So let us see what this is. So we actually define a signed distance in this way. So this is, you already know, this distance you already know, and we have multiplied it with yj. What is yj? Yj is nothing but it's the labels. So frankly speaking, this should be, j should be this side on top. This is the mistake. So yj are the labels of the corresponding data points xj. So what we are doing, we are actually multiplying the labels with the distance which we have already calculated. So if you recall, this is what? This is the hypothesis function h, or you can say the value that you will get. This is basically the equation of the separating hyperplane, and if you are putting a value of xj into this, what it is giving you? It is giving you a prediction, because it is the machine learning separating hyperplane. So if you put xj, it will give you some prediction, and this is already the label for this particular data point. You already know that yj is the label for this particular data point. So recall from our perceptron loss function also, it was also similar thing like this. If you recall, this is similar to what you have here. So what we are doing now is we are predicting. So if our prediction, which is coming from this particular part, if it is greater than 0, and if your labels are also 1, then will you all agree that this multiplied by this will always be greater than 0? So once this is positive and your machine label is also positive, then multiplying both of them will be greater than 0, and then it means you are correctly classifying the data sample xj. In the other case, when your yj is negative and your prediction by the machine is also negative, which is less than 0, then if you multiply these two together, again you will get a greater than 0 value. So it again correctly classifies the sample xj. But if it is other way around, that is, if your yj is positive and the prediction is negative, then positive versus positive multiplied by negative will give you a less than 0 value. So it will be incorrectly classified. So same goes with the fourth case, where this is negative and this is positive, or when this is positive, or when this is negative and this is positive. In these two cases, it is less than 0 and it is incorrectly classifying the sample xj. So this particular is called as signed distance, and recall that in signed distance you are multiplying it with the label. And see the similarity also with the perceptron loss. If you recall, this is our perceptron loss which we had discussed, and I have discussed the this particular function, so only this part is over here. So what is unsigned distance? Recall, in the unsigned distance you are actually calculating the distance of the points with the separating hyperplane, which is given over here, and what you are doing, what you observe is that all these distances are actually positive. So if all the distances are positive, you will not be able to find out that if this particular point, if you focus on this particular point, this is wrongly classified here because this is blue color and these data points are all green color. So if you take this unsigned distance of this particular point, which is misclassified, this is misclassified, and if you take the unsigned distance, as you know, unsigned distance is modulus, so it will always give you a greater than 0 value for this point also. And for all the other points also, it will always give you greater than 0. So that means unsigned value will not tell you whether the particular point which is here, not correctly classified, whether this point is actually error point or not. Whereas if you take the signed distance, then you can clearly see that this distance will come out to be negative, because your separating hyperplane, when you put this value into this separating hyperplane, it will give you an answer of, let us say it gives you an answer of, some plus value, this plus value, but the labels are -1. So that is important. So basically the problem is, in the signed distance, it might be the case that this particular point which you put it into the separating hyperplane, it gives you a value of plus, but your labels are -1. So that's why this particular ds equal to less than 0 will help you identify that this is wrongly classified point. So signed distance actually helps you in identifying this wrongly classified points, whereas unsigned distance cannot do that because you are taking the absolute value of that. So what is our objective? Our objective for the support vector machine is to maximize the margin. And what is the margin? Margin is gamma. What we want to do? We want to maximize this gamma. We want to maximize this gamma. So in this objective, that is to maximize the gamma, or we are right now assuming that our data set is linearly separable. That is, we have these type of cases where your data is linearly separable and it's not non-linearly separable. Please note, this particular case where we are discussing this situation is similar to the Perceptron situation, where we discussed last time also that Perceptron works for linearly separable cases and not for non-linearly separable cases. So similarly, this particular situation which I am discussing here right now is only for linearly separable cases. We will discuss for non-linearly separable cases for SVM in our next lectures, but right now it is for linearly separable cases. So here you assume data set is linearly separable and you have a constraint also. This is basically the constraint. What is the constraint? Constraint means you are bounded to follow this inequality, and constraint is what? That is yj multiplied by this, that is the signed distance, this which we are calculating already, right? This is the one which we are already calculating, and what we are saying that if it is always greater than 0 means it is correctly classifying, and if it is less than 0 it is always incorrectly classifying. So we are always taking we are saying that this value is always greater than 0. That means we are always correctly classifying the data set. That is important, and we want that value to be greater than gamma. So this condition which is over here, actually it ensures that all data is correctly classified. Why it is ensuring that it is always correctly classified? Because you know that this value is always greater than 0, because gamma is always greater than 0. So that means once you put this condition, it is inherently saying that you are ensuring that all the data is correctly classified, and you want to make sure that this value should not be greater than 0, it should be greater than some value gamma which is again not equal to 0. So that's why we want this correct classification to happen, and correct classification happens, and we want it to be greater than gamma, at least greater than the margin gamma. So basically what it says is that all the samples should be at least gamma from the boundary. So we want to select a separating hyperplane. This is our separating hyperplane. We want to actually select it in such a way that the correctly classified points which are here, if you take the distance between them, at least it should be greater than gamma. All these points which are here, these distances should be greater than gamma. So that is what our objective is, that all the samples should be at least greater than gamma. It means that if you have a data set like this, and if you have any point here which is less than gamma, it is not allowed. So this point is actually less than the margin, right? This margin is gamma, let us say, then this is not allowed at all. So this actually condition will help you avoiding the situation where you have these data points here, and all these data points will be greater than gamma. It will not allow this particular type of situation where the point is here and you are defining gamma like this. So this constraint is actually helping you to avoid these type of solutions. So where you have point, between the 2 points which is less than gamma. So this will help you out in excluding these solutions. So the problem statement that we will define now is maximize gamma, which we are discussing from the very beginning, that is gamma is the margin, right? We want to maximize it subject to this constraints. So this is basically the constraint that this particular margin has to follow. And the important point is this will actually help you out in avoiding the solutions which this particular type of problems, where the data point is here and you are selecting gamma as this margin. So it will try to avoid these type of situations, and it will also try to make sure that the data points are separated properly, because this value is always greater than 0, and it means that it is correctly classifying your separating hyperplane is correctly classifying the data. So this is actually ensuring that. So the problem is, if this is not there, what will happen is this particular machine, the SVM, what it will do is it will try to find a maximum margin where it can take this also. In this particular case, the margin is the maximum, or it can take this particular hyperplane also where the margin is maximum. But because of this constraint, what happens? Because of this constraint, these solutions will not be feasible, because this is actually forcing these separating hyperplanes to classify the data points properly. Here in this case or in this case or in this case or in this case, there are multiple misclassified data points. So the only solution which comes from this constraint will be this hyperplane, which is on vertical side, which has a maximum margin also, and all the data points are correctly classified also. So that's why we want to have this constraint along with maximization of the gamma. Any questions? Okay, so here if you see, we have three different situations which are shown over here. So in this particular case, you can see, this is the best hyperplane because it is maximizing the gamma. Here you can see this one is not a good hyperplane because this side it is not maximizing the gamma, and similarly also in this situation also it's not good because it is not maximizing the gamma here properly. So these are the figures which are actually showing you this. So our problem I am rewriting again, which is maximization of the gamma subject to these constraints. This is I have just explained you. So the problem is, this is basically an optimization problem. This is basically an optimization problem. So if you look into the books, what will happen is they will directly write this particular equation, or they will write something else also, which I will show you later on. And it's difficult for people to understand how we are getting these equations and what is the interpretation of that. So we will reach to that equation which is available in the book in a while, but to start the story, it starts from here. If you see, it starts from here. And this optimization problem is a hard optimization problem because if you see here, you are trying to maximize gamma, and in the race of maximizing this constraint also involves gamma, which also changes. So this is actually not, it's not good that whatever you maximize is also coming in the constraint. So this type of situation is not good for an optimization problem. So we will go for multiple changes in this optimization problem, so that this problem, the first problem where gamma is here also and here is also here also it is there, we want to remove this type of situation. And the second is the theta and theta 0 which you are trying to optimize are also lying in the constraints. So if you are changing theta and theta 0, because you can see that gamma is a function of theta and theta 0, which I was telling you earlier also. So if you are trying to change theta and theta 0, it is also changing here, this optimization constraint. So the problem is, even if you change gamma, this gamma changes. If you change theta 0, the subjected constraints are also changing. So again, it's a problem. So we want to make them independent of each other. That is, if you want to change this should not be affected. And the third problem is that this particular L2 norm is non-linear, because it is actually theta 1 plus theta 2 square plus theta 3 square. So it's a non-linear function. So we want to avoid this also. So there are three different problems. So we will go to multiple steps to approximate these, to avoid these problems and come up with a better optimization problem. Because this is, though it is a good optimization problem, but you cannot solve it because of these problems which I was telling you. So once we remove these problems, then you will get to the optimization problem which is available in the books. So we want to convert it into a better optimization problem. So in order to do that, the first step that we will do is we will do scaling. So in scaling, what we are doing is let xm be the closest point to the boundary. So let this be the boundary, and we are saying let xm be the closest point to the boundary, and the unsigned distance we are calling gamma tilde as this. So what we are doing, we are just putting xm in the modulus of this, and we are calling it as gamma tilde. So the gamma which we have defined earlier, so what you will do is you will replace this by this. So note that xm is actually the point which we are assuming closest to the boundary, so we are putting it over here. So now what we will do, we will actually replace gamma by this expression which we have written, that is this one. So if you write gamma by this expression, so what you get is this expression which is given over here, and once you see this theta 2 cancels out with this theta 2. So the first objective that we had is the non-linearity which was there is gone, because theta 2 is here also and it's here also, it cancels out. So what you have now is this expression. So in this expression, the next step is to eliminate gamma, because I told you, right, this is also varying, this is also varying, so we do not want to do that. So in order to eliminate gamma, what we do is we do this type of normalization which you can see over here. So what we are doing is we are actually normalizing theta by theta hat. So what we are doing, we are actually dividing this gamma tilde onto the left side. So if you divide gamma tilde onto the left side, this will become 1, and these are actually the new variables which are theta divided by gamma tilde, theta 0 divided by gamma tilde. And similarly you will have over here, and the objective function which was earlier optimizing theta and theta 0, they will now optimize theta by gamma tilde and theta 0 by gamma tilde. So now what we do is, this is basically not a problem because it's basically just a scaling problem. So what you do is you replace theta divided by gamma tilde and theta 0 divided by gamma tilde by theta and theta 0. This is just variables substitution, so it never affects the optimization problem. It is just for variable substitution. So once you do this, you will get this expression here. So what is this expression? In this expression you can see theta is replaced by theta divided by gamma tilde and theta 0 replaced by theta 0 divided by gamma tilde, and what you get now is this expression. And here in this expression you can see now that things are pretty easy now, pretty better, because gamma tilde is gone, which is actually indirectly related to theta and theta 0, and similarly your that one is also gone. The non-linearity that you had is also gone. So this is basically the objective function, and the third thing, once we are done with this, there is a slight more modification that we will do. What is that modification? The modification is that what you do now is this one, you make it come into the numerator. So now if you make this come into the numerator, what will happen is, you are, instead of doing maximization, you will do minimization. You know that if you maximize 1 by x is same as you minimize x. So, and the second thing what we are doing is we are actually dividing by 1 by 2 and squaring the terms by theta 2. So this also scaling and squaring also will not affect the solution that you will get for the optimization problem. That's why we are doing all these tricks. So these are basically the tricks which makes the optimization problem easy to solve. So if you recall, whatever solution that you will get for this will be the same solution that you will get for all the optimizations that you are seeing. But the only difference between all the optimizations which you are seeing in the top, that is this one or this one or this one or this one, that is, it is easy to get the solution for solving this particular optimization problem compared to the other cases. So this is basically the final expression for the support vector machine. This is the final expression for support vector machine which you will see in the books. And you will be surprised by seeing in the books that how this equation is coming. So the whole story which I have told you today is basically for making you understand that this is the expression for the support vector machine which they try to achieve. And by now I think you must be able to understand what these terms are and what is the objective you have for support vector machine. So we will discuss details about the support vector machine, more details about it in our next lecture. But what we observe here related to this optimization problem is that it's a quadratic minimization with linear constraints. So your constraints are linear and the objective function that you are trying to minimize is quadratic. It's a convex function and the solution to this is called as support vector machine. So if you solve this particular optimization problem. The solution to this will be support vector machine problem solution. And what is that? The solution is to get the margin which is maximum from both the sides. So we will get that solution, and it is also called as hard SVM. So we will understand what hard SVM or what soft SVM is, because this hard you must be now, you must be comfortable with it, because last time, if you recall, we were using max operator also, where you had this max operator is a hard approximation, and soft max is the softer version of that hard max, which we were calling as soft max. So we saw this type of thing earlier also. So similarly here, this particular objective function is called as hard SVM. We will understand why we are calling it as hard SVM in our next lecture. And then we have soft SVM also. So both these we will understand in our next lecture.